Alright, AP Final Exam Review Guide. So if we take a look, first one is just converting pretty simple stuff. So we have 13.2 liters to centimeters cubed. One thing you need to know is that 1 milliliter equals 1 centimeter cubed. So they are the same thing. In reality, what's called 1 liter equals 1 decimeter cubed as well. So these are two things that you should know. So if we take 13.2 liters, every 1 liter is 1,000 milliliters, and every 1 milliliter is 1 centimeter cubed. So we take 13.2 and we times it by 1,000. We get 13,200 centimeters cubed, or 1.32 times 10 to the 4th centimeters cubed. Convert 24.3 nanometers to meters. So 24.3 nanometers, every billion nanometers is 1 meter. This is common to do, to convert nanometers to meters whenever you're dealing with the wave equation. So if we take a look there, we multiply that through, we get 2.43 times 10 to the negative 8th meters. Or you could sit here and move the decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, and you would get 2.43 times 10 to the negative 8th. You would have 7 zeros behind this. How many significant figures are in this digit here? So we know this 0 is to the right of the decimal, but it is not terminating, so it is not significant. Non-zero digits are always significant, and zeros to the right of the decimal and terminating are significant. So this has 2 significant digits. Here, this 0 is to the right of the decimal and terminating, so it's significant. These digits are between 2 significant digits, so we have a total of 4, because the 1 is going to be the 1 is going to be significant because it is a non-zero digit. Here, we just have the 5, because these zeros, there's no decimal point here. These are just placeholders, so that's just 1. Here we have 2. What is the sum of all of these? Well, 32.821, 0.0034. 1 second, I need my whiteout. There we go, 0.0034. Let's do that, there you go, and 121.2. So we add all these up. 32.82 plus 0.0034 plus 121.2.
It's 32.82.
32.82 plus 0.0034 plus 121.2.
That would be 154.0234.
When adding and subtracting, you look for the least specific decimal place. So if we look, this one has the most specific decimal place. This one goes out 3 decimal places. This one only goes out 1. So we need to round that to 1. That would give us 154.0. If this were a 5 or higher, this would be a 1 instead, but since it's lower than 5, we drop everything. What is the product of 15 and 5? The product means we multiply those, so 15 times 5. 15 times 5? That's
the answer is 75.
75, which we are going to round to 1 significant digit, because the 5 has 1 significant digit. That gives us 80. So 50 plus 25, 75. Round that to 80. How many protons are in fluorine? Well, for this, we need a periodic table element. We see, take a look here. We have 9 for the atomic number. So that will be 9 protons. This is how many neutrons are in fluorine. The atomic mass for this is 19. So we're terming this as a fluorine 19 atom. Here we have the mass number. Here we have the number of protons. We subtract those. We get 10 neutrons. P plus is a symbol for protons. N naught is a symbol for, or N null is a symbol for neutrons. How many protons are in sodium plus 1? So if we take a look, sodium plus 1. Number of protons is 11 protons. That's the atomic number. Let's just imagine, let's just round this. Let's say we know that there are going to be 23, there are going to be sodium-23 isotopes. So we'll just make that 23. So the number of protons is that. The number of neutrons would be 23 minus 11, which is 12. And this plus 1 right here means that it has lost 1 electron. So the number of electrons is 10. Which we would assume, because it's an alkali metal, it tends to lose 1 electron, and it would have the same number of electrons then as neon does, because that's the electron configuration it would get. List the oxidation numbers for each atom in the following. Well, magnesium is part of 2A, so that's going to be a +2 for sure. That gives us 6 plus 2x, because the phosphorus is the one we're not 100% sure of here. 2 times 3, this is -2, so minus 6. So we get 6 minus 6. Up. 2 times 3 times 2, minus 12, not 6. It is a Sunday night. Minus 12. So 6 minus 12 equals -6. All of this has to equal 0. So 2x minus 6 has to equal 0. X must then be 3. So there we go. There we have it. That is oxidation numbers. So if we take a look here and name the following. The fact that it has an H in front of it means that this is an acid. The fact that it's an oxyacid, meaning that you have oxygen in it, means that we will change the name of this, the anion, which is sulfate. We'll take off that, minus the 8, change it to sulfuric acid. So minus the 8 and add an ic, sulfuric acid. Now if it wasn't an oxyacid, look at H2S. If there's no oxy there, then we put hydro in front of it. So that would be hydrosulfuric acid. If this were an ite instead of an 8, say H2SO3, then that would be sulfurous, again no hydro, sulfurous acid, because we changed the 8 to an us if it's an ite. I'm sorry, we changed the ite to an us, just like we changed the 8 to an ic. If it's 8, it's ic. If it's ite, it's us. And if it has hydro in front of it, I'm sorry, if it doesn't have oxygen in front of it, you put hydro in front of it. Lithium is Li, and that is lithium nitrate. Perchloric acid, well, you need to know your polyatomic ions. Perchlorate is ClO4 negative. Since it has a -1 charge, we need 1 hydrogen, because each hydrogen has a +1 charge. Remember, instead of ic, since there's no hydro in front of it, we know perchlor is going to be on the back of the periodic table or on our polyatomic ion list. That's perchlorate. If this were perchlorous, it would be ClO3 or chlorite. I'm sorry. See, if it were perchlorous, no, that doesn't exist. Let's try chlorite. Then it would be ClO2 and then an H still. Or what I was thinking of, the opposite of per is hypo, which is hypochlorite. That would be ClO negative with one H. Copper 3 phosphate. So copper has a +3 charge. Phosphate is PO4 with a -3 charge. So copper 3 phosphate would be CuPO4. Let's try copper 2 phosphate. Well, copper then would have a +2. Phosphate would still have its -3. So we would have to find the least common multiple here, which would be 6. 6 divided by 2 gives us 3 coppers. 6 divided by 3 gives us 2 phosphates. In the following, we want to know what is oxidized. Well, to do that, the easiest way is to do your oxidation numbers. So we have 0 for Fe and O2 because they're in their elemental form. -2 for the oxygen. 3 times -2 is -6. Since we have 2 ions, that must be a 3. So if it's oxidized, well, it's easier to think of what has been reduced because you would look for the number that goes down. Oxygen goes from 0 to 2, so oxygen would be reduced. Iron goes up from 0 to 3, so the iron is oxidized. Well, what is the oxidizing agent? It is what is the reducing agent? It is what is oxidized or contains the oxidized chemical, and it is what does the reducing. So iron here is reducing the oxygen. So Fe is the reducing agent as well. Page 2, what is the percent composition of chlorine in carbon tetrachloride? So basically, this is mass percent, so we have the part divided by the whole, and then we multiply it by 100. So 12.01 is for the carbon, and 35.45 is for the chlorine. Four times 35.45.
That would be 141.8.
That's our part. 141.8 divided by, nope, can't do that yet. 141.8 plus 12.01.
The answer is 153.81.
141.8 divided by 153.81 times 100.
It's about 92.1916.
Now if we wanted to find out how much carbon that would be, well, we would take 100 minus this. So what is that? 7.81. And that would tell you the percent because those percents should add up to 100. What is the empirical and molecular formula of a compound consisting of 43.6% phosphorus and 56.4% oxygen? The molecular mass of this compound, that's the molecular formula, is 284.0. So what we want to do is we want to first just change all of these, 43.6 to grams of phosphorus and 56.4% to grams of oxygen. So whatever this substance we have 100 grams of it. 43.6 grams is phosphorus, 56.4 grams is oxygen. Our formulas, however, when we look at them, they are determined by a mole ratio, moles of phosphorus to moles of oxygen. So we've got to change both of these to moles. Every 1 mole of phosphorus is something, and 1 mole of oxygen is 16.00 grams. Phosphorus is 30.97. So that will give us the moles of each of these. 43.6 divided by 30.97.
It's about 1.4078.
So 1.4078 moles. 56.4 divided by 16.
It's 3.525.
3.525 moles. So we look at these and we find the one that is the smallest. So this is the smallest one. So if we divide this one by this, we'll get 1p. And then the ratio will be 1 to something. If we divide this one also by the smallest, 3.525 divided by 1.4078.
It's about 2.5039.
So that is 1 mole of phosphorus to 2.5 moles of oxygen. We can't really have, we can have half a mole of something, but this is also like a single unit. So it's the number of P atoms to the number of oxygen atoms. So we can't have 1 atom of P to 2.5 atoms of oxygen. These need to be whole numbers. So in order to make the ratio true with whole numbers, we have to multiply each of these by 2. So that's 2 to 5. So that's the number of phosphorus to oxygen. 2 times 30.97 plus 5 times 16.
The answer is 141.94.
So 141.94 is the empirical mass. And if we take the molecular mass, which we have right here, divide it by the empirical mass, that should give us the factor that we're going to multiply each of these by. 284 divided by 141.94.
That would be about 2.0008.
So that's 2. So we multiply each of these by a factor of 2, P4O10, and that tells us then that this is the molecular formula of the substance we are talking about. Its empirical formula is found by just the ratio of each of these, but the actual molecular formula is a little bit different by a factor of 2. If a student recovered 11.5 grams of silver and started with 20 grams of silver nitrate, and 8 grams of copper, what is this percent yield? So we've got to figure out what the theoretical yield is. And as it tells us here, the equation is not balanced. So we're going to have to balance that equation. If we don't have the balanced equation, we don't know, and it says recovered Ag, so every 1 mole of Ag, can't put 1 yet, let's hold off on that. Every so many moles of Ag is so many moles of AgNO3, and every so many moles of copper is so many moles of Ag. So let's go ahead and balance that equation. So we have 2 NO3s here, so that tells us we're going to need a 2 there and a 2 there. So this is 2 moles of Ag to 2 moles of AgNO3. This is 1 mole of copper to 2 moles of Ag. So we need the molar mass of silver nitrate, 107.87 plus 3 times 16 plus 14.01.
It's 169.88.
And let's do kitty away. Let's look on the periodic table for the copper, 63.55. That will tell us the moles. We need the grams of the silver. So every 1 mole of silver is 107.87 grams. Every 1 mole of silver is 107.87 grams. 20 divided by 169.88 times 107.87.
It's about 12.6995.
8 divided by 63.55 times 2 times 107.87.
It's about 27.1584.
So out of these two, this is the amount we could make, 12.7 with correct significant digits. So we take, this is our part that they did make, 11.5 grams. This is the whole that they should have made. Part divided by whole, 11.5 times 12.7 times 100.
The answer is 14,605.
11.5 divided by 12.7 times 100.
The answer is about 90.5511.
90.55%. What is the molarity of a solution that contains 15 grams of magnesium bromide in 500 milliliters of water? So it looks like they have made a solution of 500 milliliters with 15.5 grams because it says here, ignore the change in volume due to the addition of magnesium bromide. So molarity is moles over liters. That's 2 units. So we know 15.0 grams of magnesium bromide can get us to moles, and we know that 500 milliliters can get us to liters. I'm going to go ahead and do every 1,000 milliliters is 1 liter to get rid of the milliliters. Now I've got grams and I need to change it to moles. 24.31 plus 79.90 times 2.
It's 184.11.
Every 184.11 grams of magnesium bromide is 1 mole of magnesium bromide. $15 divided by 500 times 1,000 divided by 184.11.
It's about 0.1629.
3 significant digits, so 0.163 moles per liter. Titration of 10.68 milliliters of a 0.346 molar HCl solution with a solution of LiSH required 48.2 milliliters of that to reach the endpoint. What is the molar concentration of the LiCH? So the way normally would do this is Ma Va over Ka equals Boom over Ku. Where this is the molarity of the acid times the volume of the acid divided by the coefficient of the acid. That equals the molarity of the base times the volume of the base divided by the coefficient of the base. Both of these coefficients are 1, so those will cancel out. And then we can simply take 0.346 moles of the acid times 10.68 milliliters equals, well, I want the molarity of the base, so I'm going to actually rearrange this equation. I don't usually like to do that with numbers. If I want the molarity of the base, or the molar concentration of the base, I divide both sides by VB, which is 48.2 milliliters. Milliliters cancels out. That will give me the concentration. 0.346 times 10.68 divided by 48.2.
The answer is about 0.07666.
So that gives me 0.0767, 3 significant digits, molar. State the hybridization and geometry of the element Br in BrF3. So bromine with 3 fluorines attached to it. We have 1, 2, 3. That gives us 7 times 4, which is 28 electrons. Here's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Any extra electrons we have, we put on the central atom. So that is the Lewis structure for it. So we have 1, 2, 3 bonded pairs and 2 unshared pairs, which would give us T-shaped. If we look at this, basically the pairs up here are going to force these down into that T shape. That's that valence shell electron pair repulsion theory. And we have S, P, 1, 2, 3, D. Basically, we count all of the electron regions. We start with S, and then there's 1, 2, 3, P, so P3, D. Easy enough. So here we have nitrogen. Nitrogen is in the center. I'm going to put it over here a little bit so I have more room. NO3. We have 5 plus 3 times 6.
It's 23.
So it's 23, but this -1 means we need to add 1, so that gives us 24 total. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We are 2 over this number, so that means we need a double bond. But I could choose any of these oxygens to put that double bond on, so that means this is going to show resonance. Anytime I put a double bond in, I need to get rid of, basically that was the 2 that I had extra, and then we need to get rid of the ones that are going to make up that double bond. And normally you would go ahead and put these like this, but I'll show you that in the next one. And don't forget the brackets, because that has a -1 charge. So we're going to need to draw this again. So I have it on the top one there. So then we would have this one be the single, this one the double. When we draw that, we normally would draw them like that to show how those electrons are repelling. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Then we have one more. This would be the N on the bottom. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Again, -1, -1. So if we take a look at this, remember that a double bond does not count in our hybridization. So we have our sp2. And we have 3 bonded atoms and 0 unshared pairs. So I could have drawn this a little bit better, but this is going to be trig planar. Because each of these are going to force them around. So if you were to do this perfectly or whatnot, you would draw all 3 of these just like I have, but you would want those angles to look more like they were 120. Don't forget my brackets. So here we have C and C2H2. 8 plus 2 equals 10. 1 C bond, and then the H, 2, 4, 6, 8, 10, 12, 14. Now we have 4 over, which means we need double bond at least. So anytime we put an extra one in there, we take away 1 from each. Then we take a look, 2, 4, 6, 8, 10, 12. We're still 2 over. So we need to get rid of that double bond. Boom, boom. Straight line. So that is linear, because we have a 180 there. This is pulling this straight and that straight with it. If this were over here, it would push it or force it to there with that electron valence shell electron pair repulsion theory. The angle of this would be 180. If we were to take a look, we have, remember this only counts as one, S, P. So if we take a look here, we have C and CO. It says state the formal charge of each of these. So we have C in the middle, O, that's 4 plus 12, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 4 plus 12 is 16, so we're 2 over. So we're going to need a bond there and a bond there. Then we need to take away the 2 for that bond and the 2 for that bond. So there we have our CO2. Now to find the formal charge equals the valence electrons. And you see this many different ways. I think if you've got the Lewis structure, basically you just subtract the Lewis structure electrons. But basically, people say that the number of bonds minus or divided by 2, which basically if we take these 2 bonds and divide it by 2, it would only be talking about those 2 electrons right there. So I think it's easier to just say valence electrons minus the Lewis structure electrons. Basically, you only count the ones that are being contributed from that atom. So for C, if we take a look, 1, 2, 3, 4. The valence electron number for C is 4. 4 minus 4 is equal to 0 for the formal charge. For this oxygen and this oxygen, it's going to be the same. We have 6 valence electrons. 1, 2, 3, 4, 5, 6. So for the oxygen, it will also equal 0. It will also equal 0 for the oxygen. Here we have ArF6 with a +2 charge. So that means we actually lose some electrons. So we have 8 plus 6 times 7.
The answer is 50.
50 minus 2, which is 48 electrons available. So if we put Ar in the middle, we have 6 guys here, 1 top, 1 bottom. And basically we're looking at an octahedron here. 1, 2, 3, 4. So there we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So there is our structure. If we were to do the hybridization here, we have S, P3, D2. But we don't want that. We want the formal charge. And this obviously the shape here is being an octahedron. So if we take a look for the argon, its valence electron number is 8. We have 1, 2, 3, 4, 5, 6. So 8 minus 6 gives us a 2. And for each of the fluorine, it is 7. 7, 1, 2, 3, 4, 5, 6, 7. 7 minus 7 equals 0. So again, we're looking at each of these bonds as being 2 electrons. So we want to make sure that we realize that we're only bringing the electron that this argon brought into that bond into its calculating its formal charge. How many sigma and pi bonds are in N2? There we have N. Keep in mind that if we have the 1 bond, the first bond would be the sigma bond. Those are the head-to-head bonds. And I'll go ahead with what Mr. V has written here. A single bond equals 1 sigma, and that's head-to-head, a double bond equals 1 sigma and 1 pi. The sigma is still head-to-head, and the pi is kind of side by side. And the triple bond is 1 sigma and 2 pi's. So we have 1 sigma and 2 pi's. Basically, the way we did this was like a sigma would be just a handshake. A double bond would have a sigma and a pi, the handshake and the pat on the shoulder. And the pat on the shoulder. And then the other one was kind of the crazy one. I think Sam actually got that one, but it's a handshake, the like arm grab around to the shoulder, and then another one. Basically, if you had a third arm, would basically come around, you know, the top and bottom. State the values for N and L for electrons with the following labels. So for F, so N is the principal energy level, so that is 4. If we take a look, S, P, D, F, L is 0 for S, 1 for P, 2 for D, and 3 for F. So this is N equaling 4 and L equaling 3. So again, principal energy level N equaling 2 and L equaling 0. And 2P, N equaling 2 and L equaling 1. What letter is used to indicate a shell with N equaling 3? Let's get this one crossed out for a reason. But yeah, it would be basically you start 1 is K, L, M, and like it just keeps going up like that, like the letters. Convert 39.4 liters from 167 degrees Celsius and 3 atmospheres to 60 degrees Celsius and 345 torr. I'm just going to get this right to atmospheres right away. 345, I'm sorry. Yeah. 345 divided by 760.
The answer is about 0.4539.
That's that many atmospheres with 3 significant digits. 167 plus 273.15.
It's 440.15.
With 3 significant digits. Actually, I should say significant to the ones place. So this is a, we have pressure, temperature, volume. I'm sorry, pressure, temperature, volume, and we have pressure and temperature. We want to solve for volume. So this is a P1 V1 over T1 equals P2 V2 over T2, where this is our V1, this is our T1, this is our P1, 60 plus 273.15.
It's 333.15.
This is our T2, and this is our P2. So we want to solve for V2, so we need to rearrange the equation for this. We're going to multiply both sides by T2 and divide both sides by P2. That'll cause them to cancel out over there. Let's see if I can do this just with the words, or should I write it down? I'll go ahead and write it down for this one. So we have 333.15 K, P1, 0.300 atmosphere, V1, 39.4 liters, P2, 0.4539 atmospheres, and T1 440.15 Kelvin. Notice our Kelvin and our atmospheres are going to cancel out. 333.15 times 0.3 times 39.4 divided by 0.4539 divided by 440.15.
It's about 19.7104.
3 significant digits, so we get 19.7 liters, because that's the only thing that's left. Calculate the number of liters occupied at STP by 12.4 grams of chlorine gas. So the molar volume, I'm going to move this up a little bit. Molar volume at STP states that 1 mole of any gas takes up 22.4 liters. So we have chlorine gas. Key thing is we need to realize that that's diatomic, so it's Cl2. We have 12.4 grams of this Cl2. Every so many grams of Cl2 is 1 mole. And at STP, every 1 mole takes up 22.4 liters. 35.45 times 2.
It's 70.9.
So 70.90. 12.4 divided by 70.9 times 22.4.
That would be about 3.9176.
3.92 liters. A cylinder of neon has a volume of 221 milliliters. How many grams of neon are contained in this cylinder at a pressure of 0.23 torr and a temperature of negative 54 degrees Celsius? So this is a PV equals nRT. 0.23 divided by 760.
The answer is about 0.003026.
Go ahead and change that to atmospheres. Change that to liters. We want grams, so we're going to have to get moles and then transfer that to grams. Negative 54 plus 273.15.
The answer is 219.15.
That Kelvin. So this is PV equals nRT. We're going to solve for N. So we need to divide both sides by RT. So our pressure here is 3.026 times 10 to the negative 4th atmospheres. Our volume is 0.221 liters. Our R constant, because this is an atmosphere, is 0.0821 atmosphere liters per mole Kelvin. And our temperature is 219.15 Kelvin. So here's a calculator for this one. 3.026 times 10 to the negative 4th times 0.221 divided by 0.0821 divided by 219.15. Need my scientific notation on. That's going to get me 3.717 times 10 to the negative 6th moles. And it's neon. So 3.717 times 10 to the negative 6 moles. Every 1 mole of neon equals 20.17 grams. So I'm going to multiply that by 20.17. Boom. We get, let's see here, 2 significant digits based on the torr. So we get 7.5 times 10 to the negative 5th grams. there so you can see that. Alright, let's change this around. I think I can get through gases tonight. So now I'll do the rest and add that to another video for this. So if 14 grams of NaHCO3 react with excess HCl at STP, how many liters of CO2 will be produced? So again, we're at STP, so we're going to use molar volume. Is it a balanced equation? 1 Na, 1 Na, 1 Cl, 1 Cl. Why is that Cl big? H, H, 2 H's, 3 O's, 3 O's, 1 carbon. Alright, so we're balanced. So 14.5 grams every so many grams of NaHCO3 is 1 mole of NaHCO3. And every 1 mole of NaHCO3 makes 1 mole of CO2. Every 1 mole of CO2 is 22.4 liters. So, 22.99 plus 1.01 plus 12.01 plus 3 times 16.
The answer is 84.01.
84.01. 14.5 divided by 84.01 times 22.4.
The answer is about 3.8662.
3.8662 rounds to 3.87 liters. If 14.5 grams react with excess at 6, okay, so this is at STP. So now we're saying that this grams react with excess HCl at 600 millimeters of mercury and 30 degrees Celsius. How many liters of this are produced? So what we have to do here is we have to calculate the moles, just like we did up here. So 14.5 grams, 84.01 grams is 1 mole of NaHCO3, or sodium bicarbonate, excuse me. Every 1 mole of that is 1 mole of CO2. So that will give us moles of CO2. 14.5 divided by 84.01.
The answer is about 0.1725.
And that's with 3 significant digits. So then 600 divided by 760.
It's about 0.7894.
QV equals nRT. 0.7894 atmosphere. With 1 significant digit, but I think that's supposed to be 600 exactly. 273.15 plus 30.
That would be 303.15.
So there's our P, our T, and our N. So we want to solve for volume. We divide both sides by P. 172,599 moles. Pressure 0.7894. Each of these with 3 significant digits. Atmospheres 0.0821 atmosphere liter per mole Kelvin. And temperature 303.15 Kelvin. Kelvin will cancel out, moles will cancel out, atmospheres cancel out. 0.172599 times 0.0821 times 303.15 divided by 0.7894.
The answer is about 5.4417.
5.44 liters. How many grams of KClO3 would it take to produce 15 liters of O2 at 740 torr and 25 degrees Celsius? So what we've got to do is, again, we've got to find the moles of O2 and then convert from moles of O2 back to grams of KClO3. So 740 divided by 760.
It's about 0.9736.
Atmospheres, 298.15 Kelvin. So V, P, and T, we can solve for moles again. So we know that PV over RT equals N. 0.9737 times 5.44 divided by 298.15 divided by 0.0821.
It's about 0.2163.
That's moles of O2. Every 3 moles of O2 make 2 moles of potassium chlorate. And every 1 mole of potassium chlorate is so many grams of potassium chlorate. 39.10 plus 35.45 plus 16 times 3.
It's 122.55.
0.291639 times 2 divided by 3 times 122.55.
The answer is about 23.8269.
Try that again. 0.216.
Sorry, I'm not.
0.21639 times 2 divided by 3 times 122.55.
The answer is about 17.679.
Now this is why you probably should write these things into the equation. Looks like I used 5.44 liters instead of 15. So let's try that again. That's going to make a little bit of a change for us. 0.9737 times 15 divided by 0.0821 divided by 298.15.
It's about 0.5966.
0.5966. 0.59668 times 2 divided by 3 times 122.55.
It's about 48.7487.
48.7 grams. I'm assuming this is different probably because of not rounding until the very end or going out more digits when doing that. So 48.7 grams. I usually go out 2 decimal places. I'm making the exam just like Mr. Verbrugge had it made. So if he told you to go out different decimal places on that, then definitely you should. But I'm sure that if you got 48.7 something and one of the multiple choice answers were 48.8, you'd probably be okay. A volume of 34.7 milliliters of oxygen is collected by water displacement. The water level inside the eudiometer is 19.5 millimeters higher than that on the outside. The temperature is 22 degrees Celsius. Barometer reading is 724.5 millimeters of mercury. Convert the volume to that of dry oxygen at STP. Alright, so I had to grab my water vapor pressure table for this one. So if we take a look here, we are at 22 degrees Celsius. So here's 22 degrees Celsius. Means we got a water vapor pressure of 19.8. So we got 2 things actually going on here. If we want to find this P of 1, that's first going to be equal to 724.5 minus that 19.8, which is the water vapor pressure. 724.5 minus 19.8.
The answer is 704.7.
So that gives us 704.7 currently. But then we also have to, because this is kind of a weird problem, they weren't able to equalize the pressure inside and the pressure outside. So it says 19.5 millimeters higher than that of the outside. So that means from this we also have to subtract basically what it would be considered to be like the conversion of millimeters of water to millimeters of mercury. So if we take a look on that, if you have the, how much higher are we? 19.5 millimeters higher, and that's of water. Every 13.5 millimeters of water is basically 1 millimeter of mercury on the barometric pressure. And that's basically because of the difference. This is a little bit blurry. Let's see if I can fix this. That's because of the difference of the mass. The water column of 19.5 is not going to be equal to 19.5 of the mass of the mercury column, pushing down up. So we need to do that. 19.5 divided by 13.5.
It's about 1.4444.
1.4444. 704.7 minus 1.44.
It's 703.26.
So we get 703.26. So that is our P1. 22 plus 273.15.
It's 295.15.
295.15 is our T1. .0347 is our V1. Alright, so then we're changing that to convert the volume to that of dry gas at STP. So at STP we have 1 atmosphere and 273. Actually, I'm going to go ahead and go with the millimeters of mercury here. 760 millimeters of mercury and 273.15 Kelvin. So that's our P2 and our T2. So if we have P1 V1 equals P over T1 equals P2 V2 over T2, we're trying to find V2, so I'm going to put P2 on the bottom here and T2 on the top there. And just because of that one mistake I made earlier, I'm going to go ahead and write all of these in just to make sure. So T2, 273.15 Kelvin. P1 is now the 703.26 millimeters of mercury. And the V1 coming off the page here is 0.0347 liters. I don't even know if it was worth this now. T1 is the temperature one, which is 295.15 Kelvin, and the P2 is at 760 millimeters of mercury. Let's try. 273.15 times 703.26 times 0.0347 divided by 295.15 divided by 760.
It's about 0.02971.
So 0.02971 liters. Or if we wanted to, we could have kept that in milliliters because it didn't matter. It doesn't say on this, but if we did that, we would multiply this by 1,000 and get 229.7 milliliters. If the volume of the gas is tripled while the temperature is held constant, the pressure. Okay, so if the temperature is held constant, basically we have P1 V1 equals P2 V2. So basically, if the volume of the gas is tripled, so now this is basically, we could cancel these out and we're just multiplying this by a factor of 3. That means that the P2 would be P1 divided by that 3. So it would decrease by a factor of 3. Why does increasing the volume of a given amount of gas at constant temperature cause the pressure to decrease? Basically, you have a bigger area, so there's lower number of collisions, and they're going to collide with the sides of with the walls in the container and each other less often. Remember, pressure is force divided by area. Basically, we made the area bigger, so there will be less collisions. Less collisions. Basically, if we increase the area, less collisions with the wall means lower force, which means lower pressure. At constant volume, if the temperature of a gas increases by a factor of 4, the pressure will, well, these two, if the pressure goes up, the volume had to go down, or vice versa. Here, these are directly proportional. If the temperature goes up, pressure goes up. So here, the volume went up by a factor of 3, so the pressure had to decrease by a factor of 3. Here, the temperature went up by a factor of 4, so the pressure has to increase by a factor of 4. Alright. Is that the end of gas law? Let's start that yet. Need a little bit more of gas laws. But it's getting late for me. I think I'm going to hold there. So I'm going to go ahead and stop it there. Part 2 I will make tomorrow. Alright, so 44. A law that relates volume and pressure when temperature is constant. So we know that we have the combined gas law, P1 V1 over T1 equals P2 V2 over T2. If we have temperature constant, that's going to cancel temperature out. It's the same on both sides. So that gives us P1 V1 equals P2 V2. This is known as Boyle's law. If instead of temperature being constant, if pressure is constant, we get V1 over T1 equals V2 over T2, and that's known as Charles's law. Yeah, that's it. There is one other one where volume is constant, and that would be Gay-Lussac's law. Those three laws combined bring us the ideal gas, or I'm sorry, the combined gas law. Water vapor pressure increases with an increase in temperature. So basically, we know that as you increase temperature, more particles of the water that you're collecting it over the surface of basically can go into the water vapor state of matter with the higher temperature. Basically, they have enough kinetic energy to overcome that hydrogen bonding that occurs within those water molecules. What does the term elastic, when used to describe the collisions of gas molecules, mean? So basically, when they collide, they do so elastically. There is no change in energy. Name 2 ways in which gases deviate from ideal behavior. Well, we have to assume that gases truly do have volumes. So hydrogen, its volume is very negligible to everything else. So we have to assume that gases do have a volume. Like I said, hydrogen, obviously, it's going to be very, very small. But compared to like SO3 gas or something like that, that's going to be bigger. So if you do see some changes that tend to go away from the ideal gas law, look at the gases that is going to be a bigger thing, and that volume may actually have something to do with it. The other things is gases do attract and repel. All particles do. We are taking, when we look at a gas as an ideal gas, we are taking these out of play. There is math that you could do that would bring these things back into play. That's a little bit more advanced than this course. But you do see these issues coming up if you have, for example, very high pressure. That's going to cause the gases to be closer together, where that volume can be a problem, and where attraction and repulsions are going to get higher. If you have a low temperature, we know that a lower temperature, these particles are not moving as fast as they were before. Since they're not moving as fast as they were before, that's going to, in a sense, well, we know that low temperature could lower the volume, which makes the gases closer together, which then makes them going to have more attraction and repulsion forces. More attraction and repulsion forces with that as well. And they're not moving as fast, so those repulsion and attraction forces are going to have bigger effects on them. What has more determination on the kinetic energy of a gas? Well, kinetic energy equals 1/2 mass times velocity squared. So if you double the mass, that only doubles the kinetic energy. If you double the velocity, it changes it by a factor of 4. So velocity is going to have a much bigger impact on that. If both molecules have the same kinetic energy, which one will effuse faster? If fusion is getting, like, let's say you puncture a container and that hole is there, if fusion is how fast they can get out of the hole. F2 will, because this is like, what, 70 some, and this is like 38 for its atomic mass unit. So F2 will diffuse fuse faster because of less mass. Five assumptions. Well, these assumptions, these two right here, are the first two. We assume that they have no volume. So they're small compared to the distance between them. So in a sense, no volume. High pressure, that distance between them gets a lot less, and then that volume is going to start taking effect. A low temperature, again, they're not moving as fast, and so that's you know, those forces are going to be able to do some attractive things. And that's the second one. We assume that gases do not attract and repel. Gas particles, gases do not. So 3, we can also say gas particles here as well. We assume that they are straight paths. 4, as it said above, no net change in energy, no change in net energy when they collide. Five, the kinetic energy is directly proportional to the temperature of the gas in Kelvin. So we have to remember that absolute zero is zero kinetic energy. So average KE is directly proportional to the temperature of the gas in Kelvin. Why would the water level inside a eudiometer be higher than outside the eudiometer? We try to prevent this if we can. We try to make the water level inside and outside equal, but sometimes you can't get it down deep enough. So if we take a eudiometer, and here is our water level, right here. If your gas is up here and you cannot force this down anymore into the water, then this right here is telling us that the pressure here on the surface of the outside is forcing it up into there. Just like we studied with the manometer, how outside pressure forces that liquid up into the vessel, that's what's happening here. So outside pressure is higher. And inside. Why do we divide the height by the water, height of the water by 13.5 when trying to find the pressure inside the eudiometer? So if we take a look at this, the density of H2O equals 1.0 grams per milliliter, and the density of mercury equals 13.5 grams per milliliter. So basically, for every milliliter, we have to take into account that water column, the 13.5, every milliliter of this is basically going to have 13.5 because that's the millimeter of mercury, and if we look at a barometer, it pushes the mercury up. So H2O is less dense by a factor of 13.5 times. So the weight of this water up here, we need to divide that by 13.5 to determine how many millimeters of mercury that would be equal to. What is Dalton's law? So Dalton's law of partial pressures states that the P of total equals the P of A plus the P of B plus the P of C, so on and so forth. So basically, all the pressures of each gas individually, if we want the total pressure in the system, we add up all those individual pressures. And this is why you're able to basically subtract off the water vapor pressure. Because at a certain temperature, water is going to have a certain pressure. So the pressure of the gas you wanted to know, the pressure of the gas you collected. It's going to be polluted if you're collecting it over water with water vapor. So by knowing that water vapor pressure table and the total pressure, you can subtract the pressure of the water vapor to get the pressure of the gas that you want to know. Be able to define, discuss, relate, and apply the understandings of the following. The way we're going to do this is I think that on those days of the final exam reviews, we'll cut down through these and we'll discuss them. Half and half, and then if people have more questions or whatever, we'll answer them then. Because it says be able to define, discuss, relate. So I think that has to be something that's done more actively than just watching a video of me telling. So this will end it.